physically, as I said in the first couple of classes, what is noise? Noise is the random thermal motion of electrons, and it sets up a random additive current. So in other words, if your signal current is I sub s, it will be added to a random noise current I sub n. So usually signals are large enough that I sub s completely drowns out I sub n, but for extremely weak signals, such as signals we're dealing with in communications, the noise current is actually significant, so we can't ignore it. So there is a, so how do we analyze this current? Firstly, it's Gaussian. It's a Gaussian random variable at any time. Excuse me, probably better to call it a Gaussian random process. It's Gaussian, for those who are interested, it's Gaussian thanks to a result called the central limit theorem. The central limit theorem says that if you add together a whole bunch of independent random variables, the ultimate distribution will be very close to the Gaussian. So in this case, we have billions and billions of electrons, each moving randomly and independently, all contributing to this random current. So they're very, very well modeled by the Gaussian distribution. So there is no net current, so therefore the mean of this Gaussian random process is 0. If it was non-zero, then you could gain energy out of the noise because it's moving in some direction, which would probably violate one of the laws of thermodynamics. So the mean is 0. And the power spectral density let's call this a Gaussian random process n of t. Continuous time random process. Power spectral density Sn of j omega is equal to n0 over 2. That corresponds to an autocorrelation function Rn of tau equal to n0 over 2 delta of tau, where delta is the delta Dirac function. So this is interesting. So this is one of the Fourier transform pairs you should remember. If I have a delta function in the time domain, in the frequency domain, it's a constant. So it's constant with respect to omega. So the power spectral density is constant with respect to omega. And for that reason, we call this white noise. Why do you think we call it white? What's the relationship here?
Constant.
It's constant in power spectral density. What else is sort of constant with respect to frequency? That's white. White light, basically. So we call this white noise because white light is all frequencies of light with the same strength, and this is white noise because it's all frequencies of noise with the same strength. So we take this additive, white, Gaussian, and we call this additive, white, Gaussian noise, or AWGN for short. So in discrete time, we have this. Y of k, remember that's my received signal, is generally equal to some scaling factor A, S of k. So S of k is my signal. Remember that's S0 followed by S1 followed by S0 followed by S1 and so on. That's just where my bits are. A is amplitude scaling. So that corresponds to attenuation, amplification, things like that. Y is equal to ASK plus NK. So this is my sampled AWGN process. Okay, so what are the properties of NK? Basically what we have to do in order to figure out what's going on in our detector is we have to figure out the mean, variance, and autocorrelation. Of NK. The mean, can anyone think of what the mean would be? It's 0. So I said the continuous time process has mean 0, so the sample process should also have mean 0. We need to know the variance because that tells us the strength of the noise, and we need to know the autocorrelation because that will tell us whether successive samples of the noise are independent. So that, I think, will leave there for today. Are there any questions? No? Okay. See you on Thursday.